Welcome back to the series of lectures on high-performance scientific computing. We have been looking at programming using OpenACC for multiple hardware. In this module, what we would like to look at explicit data management using OpenACC, OpenACC data regions and clauses, the structured data lifetimes, and also look at some data synchronization. So how do we go about doing explicit memory management? So what are the requirements for this first of all? The data obviously must be visible on the device when we run our parallel code. The data must be visible on the host when we run our sequential code. Remember, the host and device don't share memory, and data movement must be done, and the data movement must be done with some concurrence. To maximize performance, obviously we should avoid all unnecessary data transfers. We know that logically the host has its own host memory, the device has its own device memory, and we have to constantly transfer data from the host memory to device memory and from device memory to host memory. This transfer of data between the host and the device is a very expensive process, and we should avoid all the unnecessary ones. So many parallel accelerators such as devices have separate memory space from the host. These separate memories can be completely out of sync and sometimes can contain completely different data. While we are transferring between these two memories, this time can be very large. So for example, the CPU can have its own shared cache and then its own set of registers and then its own CPU memory. If you remember the lectures on memory hierarchy, you have different hierarchies of memory where you need to have certain synchronization. This is very similar for the device as well. Each of the device will have its own shared caches, its lower level caches, and then finally its global device memory. These are connected with some sort of input-output bus. As we mentioned earlier, transferring data between all these different levels of memories can be very expensive. But because they become out of sync, we need to synchronize them frequently. So now we will look a little bit into the OpenACC data directive. The data directive basically defines what is the lifetime of the data on the device. During the region, data should be thought of as residing on the accelerator. Data clauses allow the programmer to control the allocation and movement of data. So essentially, you'll have a pragma which says hash pragma ACC data, and you provide some clauses in the C version, C++ version of the code. So what are the different data clauses? One is copy, and the argument for this will be the list of variables. When you use the copy data clause, it allocates memory on the device, copies data from the host to device when entering the region, then copies the data to the host when exiting the region. This is primarily used for the important data structures in your code, and this is the logical default to input, modify, and return the data. If you use the copy in clause with the list of variables, it will allocate memory on the device, copy the data from the host to device when entering the region. So think of this as sort of an input when you're doing it for a subroutine. At the end, you're not going to need this particular data member. So you're not going to copy it back out from the device to the host. The copy out data clause with its arguments allocates memory on the device and only copies the data to the host when exiting the region. Essentially, think of this as the result vector. So the principal use for this is a result that is not overwriting the input data structure. And then you can always have temporary allocations using the create data clause, which only allocates memory on the device but does not do any copy either from the host to the device or from device to the host. The principal use of this is for temporary arrays. Array shaping. Sometimes the compiler needs help understanding the shape of an array. So typically the first number is the start of the index of the array. There is a slight difference in how you use it in C, C++ and in Fortran. In C, C++, the second number is always the amount of data that needs to be transferred or the number of items that need to be transferred. In Fortran, the second number is the ending index. So obviously, if the index you're starting with is 0 or 1, then this doesn't make too much of a difference. But if you're going to start from somewhere in the middle of the array, this will definitely make a difference. So in Fortran, remember the second number is the end index, and in C, C++ is the length of the data that needs to be transferred. How do you do multi-dimensional array shaping? Now, you can copy a 2D array in a similar way that you're doing a 1D array. So for example, if I look at the first example in C, C++, you're now taking an array from 0 to n in the first index and 0 to m from the second index. In Fortran, you'll have 1 to n and 1 to m. This is the example for a 2D array. But now I assume that I just want to copy only a quarter of the full array, or rather only a quarter section of the entire two-dimensional array. So I can say the same thing as array I into n by 4, and n by 4 will be now the distance of the array. So similarly, in Fortran, I'll have to give the start and end of it, so it will be I into n by 4, and the end point will be I into n by 4 plus n by 4. So when I look at the structured data directive, the parallel loop first will execute on the accelerator. So A, B, and C must all be visible on the accelerator. So that means I should have device copies of A, B, and C. So when I start, the start of the data region and the start of the end of the region is marked by the curly braces in C++. If you're doing it in Fortran, it will be the start and end regions. So what we have is, this is the region where the data clauses are applicable. Let us see what happens to the data clauses. So we have mentioned that we're going to do a copy in of A from 0 to n, B 0 with n elements being copied, and doing a copy out of C with 0 to n. So initially when the program starts, only the host memory has A, B, and C. So the actions will be, first allocate A on device, then copy A from the CPU to the device, allocate B on the device, copy B from CPU to device, allocate C on device, but we are not copying C from the host to device as yet. We then execute the loop on the device. We actually go ahead and do the calculation Ci is equal to Ai plus Bi. And then finally copy C from the device to the CPU. We do not copy A and B from the device to the CPU because we have really not modified A and B, and it makes no sense to copy back A and B from the device back to the host. That's a redundant data transfer, which can be discarded. Finally, we deallocate C from the device, we deallocate B from the device, and we deallocate A from the device, and the entire action is complete. Now let us look a little bit at implied data regions. So with every kernels and parallel region, it has an implicit data region surrounding it. So this allows data to exist solely for the duration of that particular region. All data clauses usable on the data directive can be used on a parallel and a kernel as well. So now let us figure out what is the difference between explicit and implicit data regions. If you look at these two codes, they are functionally essentially the same. The only difference is that here in the left example, you're saying hash pragma ACC data copy in, you're putting a data clause above the parallel region, and then you're putting the kernels directive. Whereas in the implicit argument, you're putting the ACC kernels and the copy in data clause together. So what's the limitation? In this case, if you look at the explicit code, you have the copy out being data clause up front, Then you have certain kernels clause where you have AI, some sort of an assignment going on. You have two separate kernel clauses. In the implicit code, you're doing a copy out for both these kernel codes. Essentially, what I really want at the end of the day and on the host side is just the final result of AI. So here I will have one data copy. In this case, I will have two data copies. Essentially, what I'm going to do on the left side with the explicit data region is that you're going to copy the array only once from the device to the host, whereas on the implicit side, you're going to copy from device to the host 2 times. Obviously, the code on the left will perform slightly better than the code on the right because you have minimized some data transfers. Now let us look at certain unstructured data directives. So the data lifetimes are always not neatly structured. The enter data directive handles the device memory allocation. You may use this to either create or copy in clause for memory allocation. And the enter data directive is not the start of the data region because you may have multiple enter data directives. The exit data directive handles device memory deallocation. You may use this for either deleting or copy out clauses for the memory deallocation. You should have as many exit data for a given array as many as enter data. This is sort of balancing the books. The enter data takes the data from the host to the device. The exit data clause takes the data back from device to the host. These can exist in different functions. So it allows the data to remain in the memory of the device for longer than necessary, or rather longer as you need it. And this can be pretty useful in minimizing the number of data transfers. So what are the unstructured data clauses? You have the copy in again, which allocates memory on device and copies data from host to device. Copy out, which allocates memory on device and copies data back to the host on exit data. Create, which allocates memory on device without data transfer to enter the data, and delete, which deallocates memory on the device without data transfer on exit data. So here's a simple basic example of unstructured data directives. So you have the same set of code where you're doing Ci is equal to AI plus Bi, and you want to parallelize this on an accelerator. What we're going to say is that you have hash pragma ACC enter, you have data copy in of the A vector, of the B vector, and then you create the C vector. And then you have the parallel loop, which will create the parallel code and execute it parallelly on the different multi-core processors. And on the exit side, you have the copy out of C and N. What will be the action? The first action would be allocate A on device, copy A from CPU to device, allocate B on device, copy B from CPU to device, allocate C on device, then execute the loop on the device, copy C from the device to the CPU, deallocate C from device, and that's it. This is an example of poor memory deallocation, because while you have finished the code, you still have A and B in the device memory, and the device memory is being consumed. So to do proper memory deallocation, you have to delete A and B from the memory. So I have to add another clause, delete AB, so that we deallocate A from the device and we deallocate B from the device. So unstructured code can have multiple starting and ending points. Structured codes must have explicit start and end points. Unstructured data directives can branch across multiple functions, but structured data directives must be within a single function. In unstructured data directives, memory exists until they are explicitly deallocated. In the structured version, memory only exists within a particular data region. So while the control is given a little bit more to the programmer in unstructured data directives, it leaves also the responsibility of deallocating memory to the programmer. So this minimizes the data transfer even a little bit more, but gives a greater responsibility of managing the memory correctly. So if you look at this particular example where enter data and exit data are in different functions, right? So this allows the programmer to put a device allocation deallocation with the matching host version. This pattern is particularly useful in C++ where structured scopes may not be possible. So if you look at this code, you will see that the function allocate array is where the data is getting entered into the device memory. The function where deallocate array is there, that's where the data is getting freed from the memory. The other important bit is data synchronization. Update. The update directive essentially explicitly transfers data between the host and the device. This is useful when you want to synchronize data in the middle of a data region. Remember, when the code is running on the accelerator or on the device, the host copies are no longer in sync with the device copies because we want to minimize the data transfer. But let's say once in a while we do want to synchronize it for some other functionality. For that, we have the update directive. The update directive also has to take two clauses. One is either self, the other one is device. If you take the self clause, it takes the host data and makes it agree with the device data. If you say device, it makes the device data agree with the host data. So these are examples of how the update clause is used. So how does the update directive actually work? So remember, you have multiple copies of the same data member. A can be resident on CPU and A is also on GPU. Similarly, B is on CPU and B is also on the device. If I say hash pragma ACC update device, then the copy which is existing in the CPU is transferred and the device memory gets updated to reflect what is there on the CPU. If I say update self, essentially what it says is that the value of B which is there on the device is now copied onto the CPU and it is updated from the device to the self, which is the host. The data must exist on both the CPU and the device for the update directive to work. Remember, there has to be both of these individual copies, otherwise it will not be correct. So this is an example where we are going to synchronize the data with update. Inside the initialize function, we are now altering the host copy of A. Once this is done, that means after calling the initialize function, the host and the device copy of A are actually out of synchronization. We then use the update directive to with the device clause to update the device copy of A. Without the update directive, the later compute regions will also use incorrect data if you did not do this update clause. We will now look at C, C++ structures and classes. So if you did not have dynamic data members are anything contained within a struct and that can have a variable size, such as a dynamically allocated array. In OpenACC, you can easily copy your struct to a device memory because everything in this particular example of a float3 struct has a fixed size. So if you look at this structure of float3, it basically has 3 floating point numbers and everything within that float is of a fixed size. Float3 itself can be of variable size. This can be easily copied. But what if the structure had dynamically allocated members itself? For example, if I have a structure where for example, vector, where I have a dynamically allocated size. OpenACC does not have enough information to copy the structure and its dynamic members. So first, you must copy the struct into the device memory, then allocate/copy the dynamic members into device memory over here. Then to deallocate, you must first deal with the dynamic members and then the structured members. OpenACC will automatically attach your dynamic members to the structure. C++ structures and classes work exactly the same way as they do in C. The main difference is now how we have to account for the implicit this pointer. Thank you.